It's my youngest's 8th birthday, so we're having our birthday party tonight, and so I haven't even cracked open the. Get a chance tomorrow. I certainly don't want to promise they'll be back by Friday. The default is going to be for me to grade them over the weekend, but if for some reason I can find some extra time, I'll try to get into them, but I don't want to rush it. What did I just do? That's not what I wanted to do. And now I can't see the window. Cancel. I'm not sure what button I clicked, but it wasn't the right one. Okay. All right, so let's, after sitting on chapter 6 for a while, which we really needed. Chapter 6 is like 2 chapters in one. There's that much material in it, and it just takes a while to sort of practice with all of those concepts. Finally into chapter 7, and I want to show the video that I'm hoping you watched with at the beginning of the slides, or excuse me, the video that you watched. And I'm assuming if I click on it, no. How do I start this here? Usually it shows me. Well, maybe I'll have to describe it, since I can't see any way to click on it. Out of presentation mode. Okay, end slideshow. Go here. Something must have happened to my videos, but I'm hoping you saw them. The video, you can sort of imagine, it's a slow-mo of a baseball hitting a steel plate over here, and the steel plate doesn't move, and the baseball comes in, and it, of course, just barely touches it, and it starts to deform quite a bit. It compresses. It's amazing. Baseballs feel pretty hard, but they can compress. Golf balls even more so. So it compresses a lot, and then it decompresses and shoots back in the opposite direction. So the idea is this was shot at a steel plate. And if we plot the force on the ball as a function of time, well, maybe I'll just try to continue in here. If we plot the force on the ball as a function of time, oh God. I'm not sure why it's doing this to me today, but I can't. There we go. If you plot the force on the ball as a function of time, it's not surprising. I mean, this is just a qualitative graph, but it might look like something that sort of starts out at close to 0 when contact begins. So we're plotting as a function of time how big the force on it is. And it goes up to some maximum. That's when it's most compressed. And then it goes back down to 0 after it leaves contact with the thing that is being compressed there. And I'm just drawing a qualitative graph here, but we could imagine how we might make, the size of this curve, how much area is under the curve, affects how big of a change in the velocity of the ball there's going to be. In other words, if I make the maximum of the curve even higher, that means the maximum force is going to be bigger. And suppose it stays, acting on it for the same amount of time. That would change the velocity of the ball even more. Or another way to change the velocity of the ball even more is to have it last for a longer period of time. In other words, maybe the maximum force isn't any bigger, but as shown by this blue curve here, maybe it just lasts for a longer period of time. So qualitatively, what I was trying to show with this is that the area under the fx versus t curve, or the force versus time curve, seems like it's related to the change in the state of motion of the ball. If you have very little area, in other words, maybe the peak of the force isn't very big or doesn't last for a very long time, then you're not going to change the velocity of the ball very much, because you just have a puny force lasting for not so long of a time. But if you make it last for a long time, it can have a big effect. And if you have a huge force, it can have a big effect. So it seems qualitatively like the area under the curve is important there. Now, the area under a curve, some of you probably know, is kind of a calculus-like concept. And so in order to avoid thinking about calculus in this class, we're going to recast the area under the curve. In other words, we're going to imagine some object contacts another object, and later on we're going to be concerned with two objects colliding with each other, and the force is going to be provided by each on the other, and the other on the one. They're each pushing on each other. So you can imagine not just things running into walls, but balls colliding with each other and bouncing off of each other. If I take this area and squash it down and widen it out, I might be able to reform it into a rectangle that has the same exact area, so that this width is the same as it was for the, the hill-shaped curve. But the height of it then defines what the average force is. So if we retake that area and reshape it into a rectangle of the same width for the same amount of contact time that the collision took place, the height of this rectangle is just the average force that was exerted. Of course, the real force was sometimes smaller than the average height. And then it was bigger for a while, but we're just interested in that average. So we're going to think of the area under the curve not as having to calculate this complicated area that's being shown under the hill-shaped curve, but we're just going to calculate it as the rectangle. So the area under the curve, we know how to calculate the area under a rectangle. It's just the height of the rectangle times the width of the rectangle. So that's the average force times delta t, where delta t is how long the collision took place for. All of that to say is just to motivate this definition, which is impulse. Impulse is unlike a lot of the other words we've been using so far, because most of the words we've encountered, we have some common familiarity with, or at least they're used in the English language commonly, like force, velocity, acceleration, weight, those kinds of concepts, mass. Impulse is not something we talk about on an everyday basis, but it's no more complicated. It's actually a pretty simple thing to calculate. So, and it's motivated by that idea that the area under the F versus T curve, and we're just going to calculate that by reforming it into a rectangle, which is to say, if we're plotting the force X component as a function of T, the area under the rectangle would just be Fx average times delta T. We're going to define that to be the X component of the impulse. I don't know why that's given the symbol J, but impulse is probably because I was already taken by something else in physics, so J was just an open, more or less open symbol. So Jx is going to be the X component of the impulse vector. So we could plot the X component of the force on an object as a function of time. Maybe there's a Y component of the force on it as a function of time from that force, and a Z component. So we might have non-zero Y and Z components of the impulse. But the impulse is just some external force is being applied to an object over a period of time. And it somehow, we'll find out exactly how in just a moment, somehow the impulse applied to that object over that period of time determines how it changes its state of motion, how its velocity changes. Now, if you look at the units on here, the units on the right-hand side of impulse is going to be force units, SI units, that's newtons, times delta T, so that's newtons times seconds. So one perfectly common unit for impulse, and usually when people are talking about impulse, they'll put units of Newton seconds on it. But you'll also find that if you rearrange the symbols, in other words, if I write out what a Newton is from F equals ma, a Newton is a kilogram meter per second squared, and then I combine that with this seconds here, you would find out that another way to express those units that's exactly the same is a kilogram meter per second. And you'll find out we're going to use both of them interchangeably. And you got to realize they're exactly the same unit. And there's no shortcut unit that people define for this. So we'll either put Newton seconds or kilogram meters per second. Usually if I'm talking about an impulse, I will tend to do Newton seconds because the very definition of an impulse is Fx times delta T, or Fy times delta T. Okay, so these are the components of a vector, and sometimes we say the definition of the impulse vector is just the average force vector times delta t. But you can think of the very definite meaning of this is these three components of it. All right, let's try from that definition of impulse, just to warm up to it a little bit. Let's try the first two parts of this worksheet. We'll be chewing away at this worksheet probably through today and Friday. If you could pass that over, thanks. Mm-hmm. In fact, you'll notice that part A is really just a review question. It's like a kinematics kind of question. You couldn't use energy methods for part A, but you can use your old friend kinematics. We're just going to need it for later parts of the problem. Mm-hmm. Okay, I'm seeing that a good number of you are putting the finishing touches on part B, at least. A is supposed to be, we're going to use kinematics to do it. the most obvious way to do this. So this object's in free fall. We're supposed to ignore air resistance, so it's in projectile motion here. And I can calculate, just because it's going to be useful, you'll see why in just a second. If I want to know its initial x velocity and initial y velocity components in the coordinate system that's described. Plus x is supposed to be the horizontal direction it's moving, and plus y is up from the Earth. So here's a cartoon of it going on the way to its highest point. Then if initial is down here when you first launch it, that's equal to 17 times the cosine of, 25 degrees, and 17 times the sine of 25 degrees. So those numbers are 15.4 meters per second and 7.18 meters per second. Okay? Why do I need those? Because I want to know how high, I want to know how much time it takes to get up there. And so what kinematics equation will help me find that time? Especially given that I don't know the height it goes to, right? If I knew the height it goes to, I might say, well, I could use y final in terms of t, right, with the t squared in it. But yeah, in this case, the vy final equals vy initial plus ay times t. I know vy final is 0. It's not going up at all right there, right? And we just calculated vy initial, and we know ay is minus 9.8 in the coordinate system we're given, right? So this would be 0 equals 7.18 plus minus 9.8 times t. And I could calculate t, and I get 0.733 seconds. Please let me know if you don't agree with my numbers, because I just calculated them right before class. Okay, that's nothing new. The point of calculating that time is that here's a period of time where a force was acting. The force we're concerned about here is the gravitational force. So I want to know what impulse, x and y components. And this is some of the way that, I'm not sure exactly how Giancarlo phrases it, but I tend to say the impulse delivered to an object by a force, or the impulse received from a force by an object. Those refer to the same thing. So here, what impulse does gravity, that gravitational force, deliver to the ball while it rises to its highest point? We've got an object over a period of time, and there's a force being exerted on it. So let's calculate what the impulse x and y components are. That's jx and jy. Okay? By definition, jx is just we're concerned that, I guess I should put a little subscript here that says by gravity. There aren't really any other forces to get confused by here, but we'll see shortly that we'll start considering all sorts of forces acting at the same time. And each one is going to deliver an impulse to the object. So we have to be very careful to, just like we did with the work done on an object by a force, we want to be very clear here what the object is that the work is being done on and what force it's being done by. So the impulse done by gravity, x component, is going to be the gravitational force x component. We have to take the average, but in this case, we don't really need to calculate the average because the force is constant, so there's nothing to average over here. Times delta t, the amount of time that it was acting for. And we're asked for the impulse delivered between here and here, and we just found that amount of time was 0.733 seconds. Now, what do you say about completing this x component of the impulse here? What number do we get when all is said and done for the x component of the impulse delivered to it? It's 0, because the gravitational force has a 0 x component. It's pointing all down in the minus y direction, right? So this is going to be 0. It's the y component of the impulse that looks like the average gravitational y component times delta t. And that, if our plus y is up, you have to specify, in order to know what this y component means, we need to know what coordinate system we're using. The gravitational force is minus 9.8 times the mass of this, mg. What is the mass? Half a kilogram? Half a kilogram. So mg, sorry, I'm doing it backwards here, g times m. That's our F gravitational Y average times delta T. That's our 0.733 seconds. And that multiplies out to minus 3.59. We put all SI units in, so we should get SI units out. And I have my choice of Newton seconds or kilogram meters per second. Usually when we're talking about an impulse, people choose Newton seconds because an impulse is defined to be a force times a time, area under the force versus time curve. Questions on that? So it's a vector. The components can be positive or negative or zero. This one happened to have a negative y component and a zero x component. But you know, you saw one in the video where there was a force with non-zero x and y components of the force. And so it worked out a little bit different there. Okay, let's go back to the slides. Okay, now, we said the way I set this up, and I'm not sure if Giancarlo does it the same way, is I kind of motivated the impulses like the area under the F versus T curve seems it has a big effect on how much of a change in velocity the object's going to have, but we want to find out exactly what that relationship is now. And this is one of those things I'm just going to skip in our classroom discussion. If you want the details, they were all in the video. There's a little derivation that went on here. But the upshot is that the relationship between impulse and how the state of motion of the object changes is called the impulse momentum theorem. Along the way, we define something called momentum. Now, that is a word that we use in English in a non-precise way, but it is the momentum vector is just the mass of the object. So every rigid object that's moving with a certain velocity at a time has a momentum at that time. And the momentum is just the mass times the velocity vector of that object at that instant. So the momentum can be changing as time goes on if something's slowing down or speeding up. That just means, by definition, the x component of the momentum at a particular time is the mass of the object times its x component of velocity, and same thing for y and z. So momentum is mass times velocity, if you like. Then the impulse momentum theorem says that the net impulse, what does the net impulse mean from the reading? What does net mean here? Because we were talking about here about the impulse just delivered by gravity. There might also be an impulse delivered by an air resistance force and a little rocket I attached to it. There might be a thrust force acting on it as it's flying through the air too. There could be lots of forces acting on an object. And in general, even when something's sliding on a table, there's going to be lots of forces, right? Someone might be pushing it. There's a normal force. There's a weight force. There's a friction force. Each one of those would have its own impulse. So what does net mean here? Yeah, the same thing it did with work, right? Or with Fnet. It just means add them all together. So the net impulse means the sum of all the impulses delivered to the object by all the forces that are acting on it. So I have one impulse that I have to add together in this big sum over here for each force that's acting on the object. When I add all those together, I get that's equal to the change in momentum of the object. So expanding it out, that means the average net force times delta t is equal to mv final minus mv initial. And whenever I write something like this as a vector equation, it looks complicated because of the vector symbols, but you can always say that's true for each of the components. So the x impulse net is equal to the change in x momentum, and the same thing for y, and the same thing for z. Okay, so here was a first impulse momentum theorem practice problem that you saw that we're not going to do right now, but it involves a hockey puck traveling on, we're going to imagine the ice is frictionless, and you're given some initial velocity x and y components it has. So the xy plane is the flat ice rink. And we're told that this constant force acts on it for 4 seconds, and I want to find the puck's final velocity x and y components using the impulse momentum theorem. And so the idea is I've got enough information to calculate the net impulse delivered to the puck during these 4 seconds, and that will allow me to calculate that v final eventually. Right? Our goal is always to predict the future, or in almost all cases, to predict the future. So when we do net here, there are 3 forces acting on the puck as it's sliding around. Actually, yeah, it's frictionless. I was going to say there's 4, but no. Without friction, there's 3 forces acting on it. So the net impulse delivered to the puck is the impulse delivered by the weight force, plus the impulse delivered by the normal force, plus the impulse delivered by this applied force. I just called that the force, the one that I gave the x and y components to up here. Now I just threw the first 2 away. It looks like here, I said this is the impulse delivered by weight plus the impulse delivered by normal plus the impulse delivered by the force that's given. And here I've just thrown the first 2 away. Why did I throw the first 2 away? Yeah, they balance each other out. So that means they were both giving individually some impulse during that time, right? The weight force was acting down in the negative y direction. The whole time it was sliding over. And so it was giving a substantial impulse to it. But the weight force is exactly equal and opposite to the normal force in this particular case, because the applied force wasn't upwards or downwards. It was in the plane of the ice rink in this case. So the weight force and the normal force balance out. One of them gave sort of an upward impulse. The other one gave an equal and opposite downward impulse. And when I add those 2 impulses together, they cancel out. So it's not that these 2 are 0. It's just that this one is the opposite of this one in terms of vectors. They're 2 vectors pointing in opposite directions. One was an upward impulse, and the other one was a downward impulse. And therefore, on the left-hand side of the impulse momentum theorem, I only have to consider the impulse delivered by the thing I'm calling the force, the one I gave the components of up here. Okay. When I calculate that, well, by definition, the impulse delivered by the force is the average force times delta t. And in this case, the average force is the same as the constant force that's given there. We don't have to do any averaging if the force is constant. Okay, and that's equal to mv final minus mv initial. This is a vector equation, so I'm just going to write out the components of this separately. Okay. In terms of x components, the x components of the left-hand side are just going to be the average force x component times delta t, and that delta t here was 4 seconds. 4 seconds times 2 newtons gives 8 newton seconds, so the left-hand side of the x part gives that. And we write that equal to m times vx final minus vx initial, and plug in m and plug in vx initial, and I can solve for vx final. And the similar kinds of things for the y components. That allows me to predict the future, the same way our kinematics equations might allow us to predict the future. And in fact, we could do this with kinematics, but it's a different way that we can approach this kind of problem with the impulse momentum theorem. In any case, the final answers there aren't so enlightening. But now that we know what momentum is, you already did from the reading and from the discussion on the video, why don't we finish up the rest of problem 1, which has to do with the definition of momentum and using the impulse momentum theorem, which I've got down here in the lower left-hand corners. See if you can finish up that problem. I'll put my answers up on the side of the board just so you can ask a question if you find out you're going astray. Oops. If you're getting stuck anywhere, let me know, and then if enough people are stuck in the same place, we'll just stop there and then come together. All right, let's come together. I know almost none of you have finished all of them, but it looks like most of you are pretty deep into that second page. So first of all, we're asked for the initial X and Y components of the ball right after it's hit or shot or whatever is going on here, fired, shot. And then final X and Y components of momentum is when it's at its highest position. Now, we already decided these were the x and y initial components of the velocity vector, and momentum is just mass times velocity. Here our mass is half a kilogram. So the initial x momentum would be 0.5 times this. That's where I got this number. Initial y momentum is 0.5 times this number. That's where I got this number. And then finally, you're just supposed to think about, well, the x velocity isn't changing. So the final x momentum should be the same as the initial x momentum, because the final x velocity isn't changing if it's in projectile motion. Whereas the final y velocity is 0, and that means the final y momentum component is 0. Any questions on C? That one's just plugging it into the definition of momentum, mass times velocity at those 2 points. D, do your results from C and D satisfy the impulse momentum vector? Well, I have final and initial momentum, and I have the impulse delivered, in this case, by gravity. And gravity is the only force that's acting during the change between initial and final. Again, here we're sticking to initial is launch, final is at the highest point. So between those 2 times, does the impulse momentum theorem apply, or is it true? So we're asking is, for example, is J net x component, is it equal to, remember that means add up all the x components of impulses delivered by different forces for the time period you're interested in, is that equal to the change in the x momentum? And also, is the net impulse y component, is it equal to the change in the y momentum? Well, we've got the initial and y and final y momentum there, so we can just check it. J net x, let's see, we already found in part B that J net x is equal to 0, right? That's what we found in part B. That I'm sorry, J net x, we found out that the gravitational impulse gave 0 impulse. Gravitational force gave 0 x component of impulse. There aren't any other forces acting on the ball as it goes. So the net impulse is equal to the impulse delivered by gravity during that period of time. So this is just 0 because gravity didn't deliver any x component of impulse. And that's equal to the final momentum minus the initial momentum. That's x components. That's 7.7 minus 7.7. So that looks like it's true, right? So at least it satisfies the impulse momentum theorem for the x components. Let's check the y components. The net impulse delivered y component, again, is going to be equal to just the y component of the impulse delivered by gravity because there weren't any other forces to deliver impulses, right? It's the only force acting on the ball as it goes from initial to final. So this is just going to be minus 3.59. And the question is that equal to PY final, which is 0, minus PY initial, which is 3.59 in SI units? Sure enough. You could check it for other times, right? We could go all the way from initial till it's just about to hit the ground, and you would find the impulse momentum. You could calculate the same things between, the firing and when it's just about to hit the ground, and the impulse momentum theorem would be satisfied. So the answer is yes there. Okay, that's D. Any questions on that? So we could have gotten the answer, for example, to C just by using the result from B and the impulse momentum theorem, but we're sort of calculating the two independently here just to check it. E, what are Vx and Vy for the ball just before hitting the ground? And that's to help you answer the rest of the question. Now suppose the ball sticks in the mud when it hits the ground. So it just comes back down and sticks in the mud. And it takes 1/10 of a second to come to rest. After it contacts the mud, it just very quickly comes to rest. What XY impulse components does the ground deliver to the ball during that 1/10 of a second period? Okay, so help me find those. I didn't write down what the X and Y components of the velocity are right before hitting the ground. So I'm going to take my initial to be just about to hit the ground. and final coming to rest. So we want to know, when it's come to rest, everybody knows what the velocity x and y components are, I hope. But before it hits the ground, we want to figure out, those are going to be our Vx initial and Vy initial for the period of time from when it's just about to hit the ground until it comes to rest. So what are the x and y components of the velocity? I'm going to call those initial, just before it strikes the mud. Yeah, I mean, the x component doesn't change the whole time. So it was going at 7.18. 7.18 meters per second. It's a flat field. Oh, I'm sorry. 15.4. Thank you. Meters per second. It's shot at 15.4 meters per second. That's how fast its shadow is going to go along the ground. It just keeps going at that rate because nothing's slowing it down or speeding it up in the x direction. Now, that's not true for the y. The y slows down and comes to rest and comes back down, but hopefully we all have the intuition now that all that happens if you're starting from a certain height and going up in that parabolic motion and coming back to the same height later on, all that happens is your y velocity component switches signs. So whereas it had a positive y velocity component to begin with, it's now going to have a negative y velocity component, but of the same magnitude, minus 7.18 meters per second. So those would be my initial and velocity x and y components, and the final would be 0, right? Vx final is 0, Vy final equals 0 for that 1/10 of a second in which it's going plop in the mud and comes to rest. Doesn't take very long. All right, so if it sticks in the ground, what x and y components, impulse components, does the ground deliver to the ball during that? So the ground is a force acting on the ball. And I want to know what x and y impulse components. And I might say, well, I could go back to the definition. Impulse is just the area under the force versus time curve. And I know the time. It's a 1/10 of a second. The unfortunate thing is I don't know anything about that mud force, right? The mud force, when it just barely contacted the mud, might be really small. And then it gets bigger and bigger as it compresses more mud. And all that happens in a very short time of a 1/10 of a second. And so to calculate the impulse directly from the definition of impulse, area under the fx versus t curve, we don't really know anything about that mud force. It's not a force that we've talked about. It definitely wouldn't be simple. So what I'm going to do is try to back it out of the impulse momentum theorem in this case. So we applied it up here, but we're going to apply it for a different period of time. Just that 1/10 of a second in which this ball is coming to rest. Let's calculate J net x component is equal to delta px. And I definitely know how to calculate this side. And so I'll be able to conclude something about this side. This isn't necessarily the impulse given by the mud only, right? Because gravity's acting while it's coming to rest too. But it's at least part of what comes on this side. And so I have some hope that I can pick out what the impulse delivered by the mud was. Okay, let's flesh it out a little bit. The net impulse is the impulse delivered by the mud. That's that contact force from the mud, x component, plus what other forces are acting on it? Well, gravity is still pulling down on it while it's going into the mud, right? Gravity doesn't care if you're diving into mud. It still exerts the same force on you. So we have the impulse delivered by gravity, x component. Remember, the left-hand side of the impulse momentum theorem is always the net. You have to add up the impulses delivered by all forces, all substantial forces, ones that we can't ignore. Okay, and I think those are the only two. And that's equal to delta px. So that's, let's see, this is a 1/2 kilogram ball, right? So m times v final minus m times v initial, vx initial, and that's 15.4 in SI units. That's my delta px side. This is what I'm after. So I can get at this if I could just calculate this and then subtract it off onto the other side. How do I calculate the impulse delivered by gravity x component during that time period where it's coming to rest, where x is horizontal? It's 0, because gravity only has a non-zero y component to its force. So gravity is not delivering any x impulse to the ball at any point in time, right? If plus y is up and x is horizontal. So this is 0. I could write it out as F gravity x average times delta t, but F gravity x average is 0 because gravity is going along the minus y direction in our coordinate system. And therefore, the impulse delivered by the mud x component is minus 1/2 of 15.4. That's minus 7.7 in SI units, Newton seconds. All right, we got lucky with the x components. Unfortunately, it's not going to work out so simply with the y components, but it's not so bad. Let's write that over here. J net y component is equal to delta PY. Let's flesh that out. That's J by the mud y component plus J by gravity y component. Have to add them all up, equals m times Vy final. Well, let's just put the numbers in there. M is 0.5. Vy final. What did I say? Vy final. Oh, I wrote something down wrong here, and you guys, so I'm sure you were all thinking it, but nobody called me out on it. Oh, 0. Yes, it is 0. I'm sorry. I'm thinking about the different part of the problem. So 0.5 times 0 minus 0.5 times 15, sorry, minus 7.18. So notice I have a minus situation going on here. Vy final itself is negative, and I'm subtracting it off, so those minus signs cancel. Okay, so this is what we're after. We're after the x and y components of this impulse. What about the y component delivered by gravity during that 0.1 seconds? It's not 0 because gravity is pulling along the y direction as that time elapses. So I have to go back to the definition of impulse and hope that I can get it out of there. That's F gravity y component average over that time period times delta t. Let's calculate that. The y component of the gravitational force is just m times g. So that's 1/2 kilogram times 9.8. It's negative because we're talking about plus y is up, and so the force y component will be negative. And the delta t is, I believe, 1/10 of a second. So I can calculate both the right-hand side and this. I think you'll find that this is much smaller than this, but it still does make a slight correction to it. And in this case, you find out that the impulse delivered by the mud to the ball in that 1/10 of a second y component is 4.08 Newton seconds. Any questions on that one? That one involved a little bit more detail. I think that's most people were working on that when I stopped you. Yes, Sam. Well, we're not done because we still have F, but I think we're done with E. All right. F asks, what average XY force components does the ground exert on the ball during these 0.1 seconds? So the idea is, maybe I can just work it out starting with this. Here's my two previous answers. This is the X and Y components of the impulse delivered by the mud. By the very definition of what that impulse means, let me erase this E here, I could say that number is equal to the average mud x component over that period of time, 1/10 of a second, times delta t, and our delta t is 0.1 seconds. So if I look at this equation right here, this equals this, that means I just need to divide by 0.1 from this number. When you divide by 0.1, you multiply by 10, so it's not surprising this minus 7.7 turns into a minus 77. I've just divided by 1/10, which is multiplying by 10. Same thing for this one down here. This would be equal to the average mud y force component times 0.1 seconds, and you divide by the 0.1 seconds, and that makes it 10 times bigger. So that's sort of, I mean, I feel like everybody's kind of low energy today, but that's okay. It's the day after the exam, and, we're deep into the semester now. It seems like, why would I care about this? But we have very little direct way that we could figure out what that force from the mud is. We haven't covered a mud force like we have normal forces and spring forces and all that. And this would be a complicated force, right? As this thing, slams into the mud and comes to rest, the force isn't constant at all, but at least we have a way to calculate what the average force was over that period of time during which it's coming to rest, which is somewhat amazing. Not something I would have known how to do otherwise. Any more questions on that part? All right. So that was C through F. There were a bunch of, at this point in the video, there were a bunch of voting questions, and I'm going to leave most of them out, but this is the one that always causes the most controversy, so it's worth talking about. Here's the situation. I've got a ball. Let me just grab something to hold on to here. Here's our ball. There are 3 different situations. I've got a ball, and it's moving at speed v, and it's brought to rest by a force. So maybe it's in outer space, right? It's zooming along at speed v, and an astronaut comes along and brings it to rest, okay? Second situation, the same ball starts out at rest, and the astronaut pushes on it to get it going at speed v in that direction. So it's sort of the opposite, right? Instead of starting with speed v and coming to rest, it's being started to go at speed v. And then in situation 3, it's the same ball was moving with speed v, and the astronaut pushed on it for a while and pushed on it for long enough they got it going in the opposite direction at the same speed v that it had originally. Right? They completely changed the direction as if it bounced off a perfectly elastic wall. And the question here is, in which case does the ball undergo the largest magnitude change in momentum? And a lot of people will choose either 1 or 2 because they think, the change in momentum, it had the same velocity in part 3, or choice 3 there. It has the same velocity in the initial and final state because you got it up to the same speed again. And therefore, the change in mass times velocity is going to be 0. Why isn't that true, just by definition of what momentum is? It is not true in the third case, where the ball is brought to rest by a force and then somehow got to go in the other direction, that in between, before it all started till after it ended, the change in momentum is 0. That's not true. The change in momentum is actually biggest in 3. And to most people, that's surprising. What's wrong about what I'm saying when I say it has the same velocity beginning and end? Yes? Right. I mean, velocity is a vector, so it has a direction. And it would be, if I had the same velocity before and after, that would mean I'd be going the same magnitude and direction. But when you change directions, you have a huge change in velocity, right? I had to change the velocity by half to slow it down, and then even more to get it sped up in the opposite direction. So the change in velocity is pretty big. And one way we can kind of illustrate that is maybe with some easy numbers and keeping track of x components. So let's imagine that the ball has a mass of 2 kilograms. I'm going to try to make the situation easy to calculate with. So I've got a 2 kilogram mass. And let's draw a little cartoon for situation 1, situation 2, and situation 3. Situation 1, the ball is moving at speed v, so here's my initial state, and here's my final state. I'm going to write over here. My initial state, it's moving at 2 meters per second. No, not 2 meters per second. Let's have it going at 1. Let's have it going at 1 meter per second. That's going to be my speed v. And then the final, it's at rest. In situation 2, it starts out at rest, and it ends up going at 1 meter per second. And in situation 3, it starts out going in this direction at 1 meter per second, and then it ends up going in this direction at 1 meter per second. That's a particular incarnation of what's being described here. Let's calculate what the change in momentum is, x component, for some particular x-axis. I guess it won't really matter, but I'll just take plus x to go this direction. And let's calculate what delta px is in these 3 cases. Okay, that's px final minus px initial. I'm not sure why I chose 2 kilograms there, but let's just go with it. Okay, so delta px is px final, so that's 2 times 1 is 2, minus px initial. Oh, I'm sorry, I'm looking on the wrong line. I was doing the second one already. Px final is 0. This is px final minus px initial. This is 0 minus px initial, which is 2. That's -2 in SI units. Its magnitude is 2. In this case, same kind of thing. I have px final, which is 2, minus px initial is 0. So its change in momentum is 2 kilogram meters per second, x component. Same magnitude. Most people agree that these seem like they'd be the same. But in this case, px final is -2. And then I've got to subtract off px initial, which is 2. And the -2 adds to the -2 and gives -4. So the magnitude of the change in momentum is biggest here compared to these two. You get double the change in momentum. For most people, that's kind of surprising, but that's useful to keep in mind. We're not talking about mass times speed. We're talking about mass times velocity. And when velocity changes direction, you have a huge change in velocity, and that means a huge change in momentum, much bigger than if you had just brought it to rest. Okay. Well, let's just talk about this one. 2 equal mass balls, one made of clay and one made of rubber, are simultaneously dropped from rest from the same height above the table. The rubber ball bounces while the clay ball sticks to the table. What did I just do with that? I've got some balls here where it's supposed to be one of them is really bouncy and one of them's not. So here's the bouncy ball, I think. Does what you'd expect it. Here's the one that's not so bouncy. It's not exactly like a clay ball, but they actually have the same mass. They kind of feel the same too, but this one, however it's made, it just loses a lot of energy. So when it falls down with a huge speed, it hardly bounces up with any velocity upward in that case. So we can imagine one made of clay and it would just go thwop onto the table and wouldn't bounce at all. That's what this is asking about. Which ball has the greatest magnitude change in momentum from just before they both contact the table until just after the rubber ball leaves contact with the table? And the idea is, well, the one that changed its velocity direction from going down fast to going in the other direction fast is going to be the one that has the biggest change in momentum. Whereas the one that went from going at that big speed to 0, when it flapped into the table and just stuck there, is going to have, you know, roughly half, as we saw in that example there. Okay, questions before we go on to problem 2 here. Yeah, so in this example has to do with a ball bouncing on the floor. And in this case, it's not going to be quite as simple as the one we did before, because before, when something was going through the air, there really was only one force acting on it. Here, there are going to be 2 forces acting on it. As a ball bounces on the table, not only is the table pushing on it during the bounce, but gravity's also pulling down on it. So there are two different forces acting during that very short bounce time, and that's what this question is concerned with. So try there's a lot of parts of this, but none of them take very much calculation. All the parts of problem 2 here. Yeah, so since we're talking about net, we can use the impulse momentum theorem and just do the change in momentum. So this would be J net Y that you're calculating here. And there's nothing happening in the x direction in this problem, so that's all that's really interesting. Well, in fact, that's all we're asked for. So let me just read the details here. It's moving down at 1.6, and then it's moving up at 1.4. So final is plus 1.4, and initial is minus 1.6.
I thought it was just the going down, but it's the whole bounce that we're doing.
Yes,
Okay.
the entire bounce from, so this is from just before it hits the table in a bounce till just after it leaves the table in that very short amount of time. Anyone else not agreeing with my answer A of 3? I'll come over and talk with you about it if you're not getting that. Yes, so the problem is you're not taking into account the components of the velocity. One of them is negative and the other one's positive, but you put them both in as positive. Because that's the final, right? The initial was going down. We were told to take plus y is up, I think, here. Yes, and then they add together. It may be that I miscalculated something. Let me check my work here. Oh, you're right. I didn't multiply by the mass. Yes, 1.5. I forgot to, got to have the m in your MV. Thank you. Should be 1.5. Now let's see what that messes up in the rest of my answers here. It should be negative because I just dropped the minus sign in the last one. Thank you. See if I can find a pencil here. So my answers below that are going to be wrong. We'll just have to calculate them. And I didn't bring my calculator either, but we'll work them out. Is it 0.01? Okay, thanks. Okay, let's come back together and finish it up together. All these calculations are actually pretty quick, but the hard part is just coming into it with the right frame of mind to know how to use the equation, either for, by definition, for the impulse or use the impulse momentum theorem. So in A, we're asked for the net impulse y component from just before the bounce till just after the bounce. And since we're asked for the net, that seems like a natural to use the impulse momentum theorem, which directly refers to the net impulse, for example, y component. And the impulse momentum theorem says that's equal to the change in y momentum. I did the change in the velocities, but I forgot to multiply by the m in the front. So in any case, that's 0.5 times y final, 0.5 kilograms times y, Vy final, which is positive because it's going up and plus y is up, minus m times Vy initial, but Vy initial is negative, and that's crucial to get that minus sign in there for the same reason it was crucial for the change in momentum is big when something changes its direction. We get a minus, these things add together and give me a large number. They're almost the same positive number, 1.5 Newton seconds. In B, we're asked for the impulse that gravity delivers to it during that very short period of time. It's not surprising it's going to be a small number because gravity is a modest force and it's a very short period of time, 1/100th of a second. So it doesn't have a lot of time. It's like on our F versus T graph, something happened during 100th of a second. Unless it's a huge force, there's not going to be much area under the curve there. So we just calculated according to the definition here. We can't use the impulse momentum theorem because that just tells us about the net. So the gravitational one is the average gravitational force y component times delta t. And the average gravitational force y component is negative mg because plus y is up and gravity's going down. And delta t was 1/100th of a second. So you multiply those out and you get something that's really small and also negative. Gravity's pulling down on it in the negative y direction during that period of time. So it's delivering a negative impulse. C asked, what force does the floor, the table or whatever it's bouncing on, give to the ball during the time of the bounce? Well, there are only really two forces that are being exerted during the time of the bounce. The floor and gravity. I already know about the net, which is the sum of the two, and I know about gravity, so I can back the other one out by saying, hey, look, 1.5 Newton seconds is equal to J net y. We already found that out in part A. That can be broken up. Net means the sum of all the impulses, so that's the impulse delivered by gravity, y component, plus the impulse delivered by the floor, whatever it is it's bouncing on, y component, during that 1/100th of a second. And we just calculated this as minus 0.049. And so therefore, I have to add that on to this side, and I would get that J, the impulse delivered by the floor, y component in my coordinate system, is this plus this, so 1.549 Newton seconds. That's what my answer should have been. Questions on that? All right, next one. What average y force component does the floor exert on the ball during the bounce? Remember, that floor force is complicated because the floor force is 0, And then right when at first the atoms of the ball get close to the atoms of the table or the floor, the force is almost zero. And then it gets bigger and bigger and bigger as the ball compresses. And then it gets smaller. So it's not a constant force at all. It's amazing that we can figure out anything at all about it, but we can if we know the impulse delivered by the floor. That, by definition, is equal to the average floor y component, averaged over that 1/100th of a second, times delta t. And my delta t is 1/100th. When you divide, and then I can solve for this by dividing this side by 1/100th. When you divide by 1/100th, you get something 100 times bigger. So that would be 154.9 newtons is that average force strength. All right. No, it gets better. No, I'm just kidding. Everybody's kind of low energy today. So it's hard to, like a lot of things, we're just chasing down definitions right now, and you start to see the value of this later on in the chapter. So with the reading you're going to do before Friday, you'll see why we're concerned about this. Why, what right now your opinion really should be, why would anyone care about something that's just named the impulse that I don't really have a use for? And we can kind of see now that it allows us to predict what a final velocity was later. We could already do it by other means. We'll see in greater detail toward the end of the chapter why we care for when we have a complicated collision between several objects. E and F we can solve without even calculating anything. We've already done the work. What y impulse component does the ball give to the floor during the bounce? The floor is giving an impulse to the ball. That means the ball is also delivering an impulse to the floor, or the earth. You can think of the earth as another big, sphere that it's colliding with. What impulse does earth receive from the ball during that bounce? Y component. I didn't write the answer up there because I didn't want to give it away, but you can just look at it and write down the answer. What is it? Somebody help me out here. This should be a D, it looks like. Yeah, it's the negative, because by definition, we already calculated the impulse delivered to the floor, the impulse delivered by the floor to the ball was 1.549 Newton seconds. But the amount of time that force is acting for is exactly the same. And by Newton's third law, the force that the floor exerts on the ball is equal and opposite to the force that the ball exerts on the floor. So all that's going to change in this calculation of how you calculate the impulse delivered by the floor is the sign of the force. We were talking about an upward force before. Now we're talking about a downward force. And so the answer in E is just the negative of 1.549 Newton seconds. Because by Newton's third law, it's an equal and opposite force that changes that average force y component. The delta t is exactly the same. What's the average force y component the ball exerts on the floor during the bounce? Again, no calculation required. We just look at the board and blurt out the answer. What is it? Yeah, negative 154.9. Again, that's Newton's third law. If the average force delivered to the ball by the floor is 154.9 newtons, the average force delivered to the floor by the ball, or earth by the ball, if you like, is the same magnitude force. That's Newton's third law, but it's in the opposite direction. That's a negative y component. So that would just be minus 154.9 newtons. Questions? All right. Let's go on. A little bit more. We're going to call it, I'm going to try to call it quits a little bit earlier than usual today, just because of the birthday party I have coming up, and Hamangi's taking the exam after class today. So one of the points of doing this exercise right here, I guess I should point out, is that we calculated two impulses, right? We had the net impulse. We broke that into the impulse delivered by gravity and the impulse delivered by the floor. And we found out that those two impulses were very different. The impulse delivered by the floor was, pretty substantial, 1.5 Newton seconds. The impulse delivered by gravity during that short period of time was puny, 0.049 Newton seconds. Comparatively speaking, it's a very small impulse. And so it seems like maybe we could ignore the impulse delivered by gravity in certain circumstances. And in fact, we are going to do that using something called the impulse approximation. The impulse approximation concerns itself with very quick collisions between things. So like this quick bounce on the floor, or when two objects collide in a very quick collision and they bounce off of each other. We're going to be concerned with those kinds of collisions where there's a contact force between two surfaces. So we're not talking about springy action at a distance forces like gravity, but rather contact forces where the surfaces come together and they exert huge forces on each other, but for a very short period of time. Now, the impulse delivered can still be big, right? It's a very short period of time, but if the force is huge, I can still have a big area under the curve, even though the amount of time is small. Whereas, if we're talking about, for example, these two balls are going vertically, one's going down, one's going up, and they bounce off of each other. Who knows what happens in the final state? But there are two forces acting on each one of these balls during the time of the collision. One is the contact force from the other ball, and we're going to find out that that contact force is huge compared to the force that gravity is exerting on this ball. That contact force, it way overshadows what gravity is exerting. And therefore, the period of time is so small that gravity's impulse is negligible. The same will be true for like frictional forces. If things are sliding on a frictional surface and collide in a quick collision, the friction forces will deliver a negligible impulse to each of the colliding objects. Okay, so here's the statement. In a quick collision, there can be many forces that act on each of the colliding objects. Contact forces in the collision, that's the one where the two surfaces push on each other. Gravity, friction if they're sliding on a surface, air drag if they're moving through the atmosphere, lots of different forces. During a typical collision where there's a very quick collision and the surfaces are colliding, typically those other forces, the non-contact forces, are negligibly small compared to the contact force involved in the collision, the two surfaces, how hard they push on each other. And therefore, the impulse delivered by gravity, air resistance, kinetic friction if they're sliding on a surface when they collide, those impulses are all negligible compared to the impulse delivered to each by the other one's contact force. And that's called the impulse approximation. The impulse delivered by each of the non-collision contact forces is negligible as long as we're going to take our time from just before contact begins to just after contact ends. And it's a very short period of time where the two things are just very quickly bouncing off of each other. Okay? And the idea is the other smaller forces, they're much smaller than the contact force, and they just don't have enough time to deliver a substantial momentum. If you've got a moderate force, you need a long enough time to get enough area under the curve. But if you've got a huge force, and these contact forces can be really big when two surfaces slam against each other to substantially change the impulse during that amount of time. Okay, so the impulse approximation is involved in exercise 3, A through D. We saw an example of it in exercise 2 that we just did, where the impulse delivered by gravity was really small. Now we're going to make use of it and just assume that it's true. So here we've got a 1 kilogram mass falling down at a certain instant and a 3 kilogram mass that I've thrown upward at the same time, so they're on a collision course, just traveling vertically. Just before they collide, the 1 kilogram mass is falling at 5 meters per second, the 3 rising upward at 7 meters per second. And at the instant just after a very quick collision where the two just slam into each other and then move apart, the 1 kilogram mass is rising upward at 10 meters per second. Okay, and we're going to find out something about what the other one, the 1 kilogram, the 3 kilogram is doing afterwards. Okay, so try to answer those questions. We're not going to do part E yet because we haven't talked about momentum conservation, but let's do A through D, which just concern the impulse momentum theorem. If you're not sure how to start A, notice the word we're asked for the net y impulse, and that's always suggesting that we should use the impulse momentum theorem, which talks about the net impulse delivered to an object during a collision. Okay, let's get into it together. So again, we have a 3 kilogram mass rising. Let's just draw a picture. It's always good to, when you're doing this kind of stuff, to draw the before and after picture, just so you can label things. I've got a 1 kilogram mass falling and a 3 kilogram mass rising, and we're given those speeds here, 5 and 7. So this is going down at 5 meters per second. This one's rising up at 7 meters per second just before the collision. And just after the collision, we're told that the 1 is rising up at 10 meters per second. And, well, I don't know, the 3, I'll just put a little question mark there. I don't know what its final velocity was. We weren't told it, but we're going to find it out. Okay. A, what net y impulse does the 1 kilogram mass receive during the quick collision? Well, that's easy. I know it's initial and final momentum components. I think we're told plus y is up here. Yes. So if I want in A, the impulse, net impulse delivered to or on the 1 kilogram mass, y component. Trying to put a big subscript on there to make sure I remember what this means. Well, it's the net, so that's equal to the change in momentum y components of the 1 kilogram mass. That's equal to the y momentum in the final state minus the y momentum in the initial state. So in the final state, it's moving at 10 meters per second, and its mass is 1 kilogram, right? Minus 1 kilogram times its initial velocity y component, and that is minus 5. So then the 10 adds to the minus 5 to give 15 in SI units. And as always, I'm being lazy by leaving out the units, but I know I put all SI in, and therefore I'm going to get SI out. SI units for impulse is 15 Newton seconds. Okay, we've done that kind of stuff before. Here's where the impulse approximation comes in 2. Let's assume the impulse approximation applies, so that during this collision, the force on the 1 kilogram wasn't just the contact force from the 3. Certainly that's one force pushing on it, but gravity was pulling down on it the whole time too. And maybe air resistance was non-negligible during that amount of time too. But we're going to assume that those forces, compared to that contact force that gets really big really quickly as they slam into each other and push apart, air resistance just doesn't have enough time to deliver a big impulse. Neither does gravity. Even though gravity can be a moderate-sized force, it doesn't have enough time. It has to be a huge force. So we're going to assume that the net impulse delivered to the 1 kilogram is equal to the contact force delivered to the 1 kilogram. Okay. Using Newton's third law, what y impulse does the 3 kilogram mass receive from the 1, or delivered by the 1 to the 3 kilogram mass? There are different ways to phrase this. So in B, to write it down in symbols, what I want is the impulse y component that is delivered. How did I write it down here? The impulse by the 1 kilogram on the 3 kilogram, just to make it unambiguous. And it's a y component of an impulse. Okay, the force is on the 3 kilogram. And the idea is, well, I don't know anything about forces or impulses on 3 kilograms, so let's relate that first back to an impulse being delivered to the 1 kilogram. Isn't that equal and opposite to the impulse delivered by the 3 kilogram to or on the 1 kilogram y component. Those y components are going to be opposite because the amount of time that they took place is the same, but the force y components are going to be equal and opposite, right? Because those contact forces are a Newton's third law pair. Okay. Now, this is approximately equal to the, I'll keep the minus sign, but this symbol here for the impulse, by the impulse approximation, is almost the same thing as the net impulse delivered to the 1 kilogram y component. Why? Well, in the net, there were several forces that were delivering impulses. The contact force from the 3 was one of them. There might have been gravity, there might have been air resistance, but we're just going to ignore those and assume that they deliver a negligible impulse during that short period of time from just before contact to just after contact. Okay, so this is approximately equal to everything that goes into the net. And I can calculate that, well, I guess we already have that, right? We've already calculated it up here, so that's just minus 15 Newton seconds. So that's B. C, I can use the impulse momentum theorem to calculate the y velocity of the 3 kilogram mass after the collision. How would I do that? Yes, Andre? Right, we're interested in the the y velocity of the 3 kilogram mass, and that's going to come into the impulse momentum theorem for this one. So we just found out that the impulse delivered to the 3 kilogram mass, which is approximately equal to by the 1 kilogram, is approximately equal to J net on the 3 kilogram during that collision process, y component. And that's equal to the change in momentum of the 3 kilograms. So that's let's see, it's 3 kilograms times Vy final of the 3 kilogram minus 3 kilograms times Vy initial for the 3 kilogram. And what was that? 7 plus 7. We got to be very careful of signs here, but plus y is up. It was going up initially, and therefore I have that. So here's an equation. Looks like this. Let's see if we did this correctly. So if I have, let's see, 21 over here, bring it over to this side would be a plus 21. Minus 15 is 6. And then I've got to divide out this 3. 6 divided by 3 is 2 in SI units for the Vy final of the 3 kilogram mass, 2 meters per second, just solving that equation that I looped around there. All right, and let's just finish up with D. If the collision lasts 0.03 seconds, 3/100ths of a second, what average y force does the 1 kilogram mass exert on the 3 kilogram mass during that amount of time? And I already know the impulse delivered by the 1 kilogram mass to the 3 kilogram mass, right? Let me make sure I'm reading them correctly. Oh, yeah, on the 3 kilogram mass by the 1 kilogram mass. So we're concerning ourselves with this impulse right here. And we can say, I know what this impulse is. It's minus 15. That's equal to the average force y component of the 1 kilogram on the 3 kilogram, averaged over that time period, y component, times delta t. And we're told the delta t here is 0.03 seconds. So if I set this equal to minus 15 and divide out the 0.03, apparently I get minus 500 in SI units, which is newtons. All right. since I want to call it quits early today, and it seems like you guys are really tired as well, or maybe it's the material or something, I don't know. But it could be the post-test blahs. But in any case, we're going to get more to the point of this on Friday, and tomorrow we're going to be talking about the impulse momentum theorem in lab. And in fact, we're not going to be doing the easy case where we have a constant force acting like gravity. We're going to have a contact force, or something like a contact force, that's smaller and then gets bigger and then gets smaller again. And we're actually going to find the area under the force versus time curve, but using some software that does the calculus for us. So we'll just visualize it and it will tell us the number for the area under the curve. So come to your usual section of lab tomorrow, either the early or the later section. And I'm looking forward to that. We get to use our air tracks, the frictionless tracks, to help minimize the amount of friction. See you then.
I actually saw a pretty cool video that I think is about collision, where there's two blocks that one that is moving and the other one's still, and it bounces off a wall. And the amount of bounces that it does equates to pi. If it's like 10, like if this one's 1, this one would be 10. It would bounce 3 times. If this one was 100, it would bounce 31. If this one was 1,000. That's 314.
Now what was this? What kind of ball is it? Because clearly it depends on how.
2 blocks, and it's like a frictionless plane, and it's just sliding at some constant speed. I don't know if that's important or not, but and then the small thing, when it hits the smaller one, it bounces it into the wall. But this one keeps moving because it's heavier, and so it bounced that many amount of times.
Yeah, it's not clear from the outset why pi would be involved in that at all to me, but. Interesting.
I just want to tell you that me and Natalie are going to.
Yeah, I talked to her about it, and she said that's good to push it back for a day. All right, so we'll do it on Friday. See ya. Let's do it over in the lab room because I still have some setup to do for tomorrow's lab, so that will actually be more convenient for me. You're welcome. See you tomorrow.